This is SpaceTime Series 28, Episode 147, for broadcast on the 15th of December, 2025. Coming up on SpaceTime, NASA loses contact with its Maven Mars orbiter, how the cosmic landscape impacts a galaxy's life cycle, and a new study suggests the planets Uranus and Neptune might be rock giants rather than ice giants. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
NASA has lost contact with its Mars Atmosphere and Volatile Evolution, or Maven, spacecraft. The agency says the probe disappeared off the proverbial screens on December the 6th. At the time, telemetry showed Maven was working nominally as it passed behind Mars as seen from Earth. But the spacecraft didn't resume communications after emerging from behind the planet. Mission managers are now investigating the anomaly and are yet to determine what's gone wrong. The orbit has been circling the red planet for more than a decade, gathering scientific data and serving as a key communications relay satellite. Maven launched back in November 2013 and entered orbit around Mars in September 2014. The spacecraft's primary mission has been to study the planet's upper atmosphere and interactions with the solar wind, including how the atmosphere escapes into space, helping scientists better understand how the red planet changed from a warm, wet world with a thick atmosphere, one capable of supporting liquid water on its surface, and turning it into the inhospitable freeze-dried desert it is today. This report from NASA TV.
Today, Mars is a cold, dry world with a tenuous atmosphere, only 1% as thick as Earth's. But in the ancient past, water flowed freely across the Martian surface, maintained by a thick, early atmosphere. Since it first arrived at the Red Planet in September 2014, NASA's Maven spacecraft has been studying how that atmosphere was lost to space, and with it, the water. In 2015, Maven observed the solar wind eroding the Martian atmosphere. The solar wind is a stream of electrically charged particles blowing from the sun. Maven watched as ions from the Mars upper atmosphere were accelerated by the solar wind's magnetic field and driven into space, confirming that this process has deeply eroded the Martian atmosphere. In 2017, Maven showed that a process called sputtering has had an even greater effect on the atmosphere. When ions from Mars get picked up by the solar wind's magnetic field, they can crash into neutral atoms at the top of the atmosphere, sputtering them into space. Maven measured present-day isotopes of argon, which can be removed only by sputtering, to determine that 65% of the noble gas has been lost over time. This allowed scientists to estimate the escape of other gases and determine that sputtering has been the primary mechanism driving the atmosphere into space. Later in 2017, Maven revealed a twist in Mars's invisible, magnetic tail. When the sun's magnetic fields reach Mars, they pile up and wrap around the planet, creating an induced magnetic field that is drawn out behind Mars like a comet's tail. The Martian crust also contains small pockets of its own early magnetic field, which rotate along with the planet. Maven discovered that when these two fields interact, they put a twist in the magnetotail, confirming model predictions. In 2018, a runaway series of dust storms created a dust cloud so large that it enveloped the planet. During this global dust storm, Maven observed an abrupt, unexpected spike in the amount of water in the upper atmosphere. It discovered that heating from dust storms can loft water molecules far higher into the atmosphere than usual, leading to a sudden surge in water lost to space. Later in 2018, Maven announced the discovery of a new type of aurora at Mars. The mission had previously observed auroras during solar storms after electrons from the sun struck the upper atmosphere, causing it to glow with ultraviolet light. Maven's 2018 discovery was the first observation of a Mars proton aurora. When protons from the solar wind pick up electrons from the Martian ionosphere, they can slip through the planet's bow shock and plunge into its upper atmosphere, causing widespread auroras. On Earth, proton auroras are isolated near the poles, but on Mars, they can bathe the dayside in ultraviolet radiation. In 2019, Maven produced the first map of wind currents in the Martian thermosphere, revealing disturbances in high-altitude winds caused by terrain features on the surface. Maven sensed these disturbances as it skimmed through the upper atmosphere, feeling the imprint of mountains and valleys far below. In 2020, data from Maven led to the creation of another new map, showing the Martian atmosphere's electric current systems for the first time. Maven detected these currents indirectly by observing the solar wind's magnetic field lines drape around the planet. Mapping the electric current systems can help scientists to better understand the forces that drive atmospheric escape. In 2022, Maven watched as the solar wind unexpectedly disappeared from Mars. The event occurred when a fast-moving patch of the solar wind overtook a slower-moving region, leaving a void in its wake. In response, the Martian magnetosphere ballooned outward by thousands of kilometers, engulfing Maven's orbit and causing the solar wind to temporarily disappear from view. In 2022 and 2023, Maven captured stunning ultraviolet images of Mars when the planet was near opposite ends of its elliptical orbit. The first image was taken when the southern hemisphere was in summer, which coincides with Mars's closest approach to the Sun. Canyons and basins are covered with a thin haze of ozone, indicated by a tinge of pink. The second image was taken during northern spring, after Mars had passed its furthest point from the Sun. White clouds hint at rapidly changing conditions in the northern polar regions, while deep magenta signals a buildup of ozone during the frigid winter. In 2024, Maven observed the aftermath of an X-class solar flare, the strongest type of eruption from the Sun. The flare was quickly followed by a burst of charged particles crashing into Mars, leaving black and white streaks on images taken by NASA's Curiosity rover. Maven watched from above as auroras lit up the planet in a brilliant display of celestial fireworks.
Maven's other role as a communications relay satellite has provided a key link between both the Mars Curiosity and Mars Perseverance rovers down on the Martian surface and mission managers at the Jet Propulsion Laboratory in Pasadena, California, by way of NASA's Deep Space Communications Network ground stations in Goldstone, California, Madrid, Spain, and Canberra, Australia. NASA's Mars Odyssey spacecraft and Mars Reconnaissance Orbiter also serve as communications relays for the rovers, but both are significantly older than Maven. And this isn't the first time that Maven has suffered technical issues. Back in 2022, the probe's inertial measurement units, which are used for navigation, failed. That forced mission managers to switch the orbiter to a stellar navigation system, minimizing reliance on the inertial measurement units. Maven has enough propellant to maintain its orbit through at least until the end of the decade. This is SpaceTime. Still to come, how a cosmic landscape can impact the galaxy's life cycle. And a new study suggests the solar system's two ice giants, Uranus and Neptune, might actually be more rocky than icy. All that and more still to come on SpaceTime. A new study has shown how a galaxy's neighbourhood can influence its evolution. The findings, reported in the monthly notices of the Royal Astronomical Society, offers a new level of detail into science's understanding of galactic evolution in the distant universe. The research is based on data from DEVILS, the Deep Extragalactic Visible Legacy Survey, an extensive galaxy evolution survey which shows that a galaxy's local environment plays a major role in how it changes over time, strongly influencing its shape, size, and even its growth rate. The survey combines data from a wide range of terrestrial and space-based telescopes to investigate various aspects of astrophysics by analysing hundreds of thousands of galaxies. The project lead, Luke Davies from the University of Western Australia node of the International Centre for Radio Astronomy Research, says the DEVILS survey is unique in that it's the first of its kind to explore detailed aspects of the distant universe. It focuses on galaxies that existed up to 5 billion years ago and examines how these galaxies have changed through to the present day. He says, while previous surveys during this period of universal history have explored the broad evolution of galaxy properties, they've inherently lacked the capacity to determine the finer details of the cosmic landscape. The Devil survey has allowed astronomers to zoom in and focus on mapping out the small-scale environment of galaxies. This new approach has allowed Davies and colleagues to identify the number of stars in a galaxy, understand ongoing star formation, and analyse their visual appearance, shapes and structures. They can then compare these properties between galaxies in the present-day universe with galaxies that existed around 5 billion years ago, in order to determine how galaxies have changed over time. They found that galaxies that are surrounded by lots of other galaxies, one might say the bustling centres of galactic cities in the cosmos, tend to grow more slowly and have different structures compared to their more isolated counterparts. In crowded regions of the universe, galaxies interact with each other and compete for resources such as gas to form new stars and grow. Davies says this competition can impact their evolution and in some instances cause star formation to slow down earlier than expected, causing galaxies to die.
It's a survey that's primarily based around observations which are done with the Anglo-Australian telescope in New South Wales. So what we do is we pick a few patches of the night sky and we take a lot of imaging data that currently exists in those regions and we put it together to build a sample of galaxies that we want to explore. And then we go to the Anglo-Australian telescope and we measure spectra for all of those galaxies. And what that primarily allows us to do is to measure the three-dimensional structure of the universe. So we map out the distances and the positions of all of the galaxies, and then we determine what the structure looks like. And we use that structure to work out places in the universe where there are lots of galaxies, so very sort of over-dense regions, which are sort of bustling city centres of the universe environment. So they're mostly galaxy groups, which are slightly smaller than clusters. So
sort of like
given the volume, so sort of from the local group size up to a little bit bigger, mainly because of the volumes that we probe are quite small in comparison to the nearby universe. So you actually don't get some of the really massive cluster type things. Then what we do is we try and combine all the information about what the galaxy's local environment is like, so how clustered the regions are, and link that up with the properties of the galaxies to see how where they live is impacting their life cycle.
And what have you found?
What we found is that when you start to map out the universe on this sort of smallish scale in terms of environments, that the properties of galaxies are very strongly linked to where they live in the universe. So if you grow up in bustling sort of city centres of the galactic environment, you actually die more easily, you form less stars, you look different, you grow in a different way to if you live in a sort of isolated, remote region of space.
I would have thought that if you're in a busy, bustling area with lots of other galaxies, it'd be easier to steal gas from them and make more stars and even grow bigger because you can merge with them. That's not what you found, but...
So that's largely true for the sort of big central galaxies in those environments. We tend to split galaxies in those environments to centrals and satellites, where central is sort of the main big galaxy in the middle, and the satellites are all the other ones which are moving around it. So for the central region, being in that overdense environment actually helps it to grow more massive. But for the satellites, it actually stops them from forming new stars so that they don't grow any bigger. And all of those interactions with the other galaxies actually change the way the galaxy looks as well. So we define how a galaxy looks as something called morphology, which basically defines whether it's sort of a big blobby red structure or a disc-like spiral structure. And where a galaxy lives in its environment and its interactions with other galaxies changes the type of morphology that galaxy is.
Is that why the large and small Magellanic Clouds are disrupted spirals or irregular spirals rather than grand spirals like, say, the Milky Way? Or?
Yeah, so they're also much smaller. So these sort of smaller regular galaxies tend to form as more sort of blobby structures. But yeah, their interactions with the Milky Way will make them look different. So imagine if you have say you have two big spirally type galaxies and you smash them both together, you end up with something that looks more like an elliptical galaxy. And because those processes are happening more readily in group environments, you end up getting more elliptical-like things in group environments than you would in isolated environments. The real benefit of what we've done with Devils in this is that this type of science of mapping out the sort of group scale, so the much lower mass scale than clusters environments, has only previously been done in the relatively local universe. The reason for this is that to be able to map out the three-dimensional structure of a universe, you need to measure redshifts, basically, for lots of galaxies to get their distance. And doing that outside of the local universe is really problematic because you have to observe for a really long time to get enough signal to noise to measure the redshift. So we've done this in the local universe with other surveys. But with Devils, what we've done is we've stretched that out into the much more distant universe by observing the same galaxies for much longer time, basically, to get their redshifts. So it's the first time we've really managed to map out this sort of group scale structure in the very distant universe.
And you're moving from Devils to Waves next.
Yeah, so Waves is a survey that's going to be starting next year on a new facility which is called Foremost, which is the 4-meter multi-object spectrograph telescope, which is in Chile. And what we're doing with Waves is that we actually have a few different sort of surveys that we're doing, but one of the components of Waves, which is called Waves Deep, is basically the same as Devils, but over a much, much larger area. So essentially, we'll be doing all of the science that we can do with Devils now, but to a much, much finer degree over much larger volumes of the universe. We actually have got the first test observations from Foremost for some of the galaxies in Waves, which has been really exciting. So we've all been working away to try and understand everything that's going on with the telescope, and then we'll start Waves in earnest next year.
One of the big topics of recent papers that I've seen has been this ongoing hypothesis that the Milky Way may not be within a strand of galaxies in the cosmic web of the universe, but rather it may actually be at or near the edge of a large void. Has your work in any way at all helped resolve that issue?
The issue of this is that some of our results in terms of our cosmological analyses, so analyses of how the whole universe works essentially and how the whole universe is evolving, are a little bit in tension with each other. And one of the possible solutions for that is that we live in a slightly atypical part of the universe, so next to a cosmic void, which would mean that some of our measurements that we use to infer cosmological principles are a little bit wrong, because all of those assume basically that we live in a very representative place in the universe. Now, it is really super interesting, but it's not really something that I work on massively. I look at galaxies which are much, much further away than that local volume. But there is an Australian-led survey that's going to be happening on Foremost as well, called the 4HS, which is being run from the country, which will actually test some of these things about the distribution of galaxies in the very local universe as well. So I would say hold tight, and in sort of 4 or 5 years' time, when we have results from Foremost, we might be able to say something a bit more about this problem.
The reason for this assumption that we're in on the edge of a void is simply because of studies looking at expansion of the universe based on dark energy.
Yeah, so that's one of the cosmological measurements that I mentioned. So there's currently just this tension as to how dark energy is evolving and whether it's changing with time or whether it's a constant. And one of the potential solutions to all of this conflict is that we live within this void, which actually allows you to match up some of the sort of slightly disparate observations that you get from doing different measurements.
Yeah, it's a small void if it is a void. But,
yeah.
The interesting thing is, of course, there have been some new results that have just come out showing that dark energy isn't constant, but in fact we have not just reached the maximum extent of dark energy, but it may be going in reverse now. Yes,
so most of those results are coming out of a survey called DESI, which is done in the northern hemisphere. And not to bang on about Foremost too much, as a pretty amazing instrument when it starts going, but there's also a different survey that's going to be done on Foremost, which is a survey which is similar to DESI, but will be in the southern hemisphere. So when that's done, combining the data from DESI and this Foremost survey in the southern hemisphere will actually produce way better constraints on all of these measurements. So it's quite exciting that we might have sort of DESI times 2 in about 5 years' time, where we get much better constraints on all of this, and we'll probably then get a definitive answer onto whether dark energy is changing with time or is constant.
That's Associate Professor Luke Davies from the University of Western Australia node of the International Centre for Radio Astronomy Research. And this is SpaceTime. Still to come, a new study suggests the solar system's 2 ice giant planets, Uranus and Neptune, may actually be more rocky than icy. And later in the science report, a new study warns insufficient sleep may shorten your lifespan. All that and more still to come on SpaceTime. A new study suggests the solar system's 2 ice giant planets, Uranus and Neptune, might actually be more rocky than icy. The findings follow new computer simulations examining the likely internal structures of the 2 worlds. Now, this new study isn't claiming that these 2 blue planets are one type or the other, water or rock. Rather, it simply challenges the idea that ice-rich isn't the only possibility. This new interpretation is also consistent with the discovery that the dwarf planet Pluto is rock-dominated in its composition. The planets in our solar system are typically divided into three broad categories based on their general composition. There are the four terrestrial rocky planets, Mercury, Venus, Earth and Mars. Then the two gas giants, Jupiter and Saturn. And finally, the two ice giants, Uranus and Neptune. Now, according to the new work carried out by the University of Zurich scientific team, Uranus and Neptune might actually be more rocky than icy. The study's lead author, Luca Morf, says the ice giant classification might be an oversimplification, but he admits both worlds are still poorly understood, and models on the two based on physics are too assumption-heavy, while empirical models are too simplistic. Morf and colleagues combined both approaches in order to get internal models of the two planets that are both agnostic and physically consistent. Now, to do this, they first started with random density profiles for each planet's interior, based on a numerical framework. They then calculated planetary gravitational fields in a way that was consistent with the observed data available, and that allowed them to infer a possible internal composition. Finally, the process is repeated to obtain the best possible match between models and observational data. And the authors found that the potential internal composition of the pair isn't limited to mostly ices. Instead, a new range of internal compositions show that both planets can either be water-rich ice or rock-rich material. The study has also brought a new perspective on both Uranus and Neptune's puzzling magnetic fields. While the Earth has clear north and south magnetic poles, the magnetic fields of Uranus and Neptune are far more complex and include more than just two poles. The new models show ionic water layers which generate magnetic dynamos at locations that help explain the observed non-dipolar magnetic fields. They also found that Uranus's magnetic field originates far deeper inside the planet than that of Neptune. While these new results are promising, uncertainty still remains. One of the main issues is that physicists still barely understand how materials behave under the exotic conditions of pressure and temperature which are found at the heart of a planet, and that will impact results. Still, despite the uncertainties, these new results are paving the way for new potential interior composition scenarios which are challenging decades-old assumptions and which could guide future research into planetary conditions. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. A new study warns insufficient sleep may shorten your life. The findings, reported in the journal Sleep Advances, compared sleep patterns with life expectancy. And the authors found that as a behavioural driver for life expectancy, sleep stood out far more than diet, exercise, loneliness, and indeed more than any other factor except smoking. For the study, the CDC, the Centers for Disease Control and Prevention, defined sufficient sleep as at least 7 hours per night, which is recommended by the American Academy of Sleep Medicine and by the Sleep Research Society. Although previous research has shown broadly that a lack of adequate sleep does lead to higher mortality risk, the new research is the first to reveal year-to-year correlations between sleep and life expectancy. The World Meteorological Organization says there's now a 55% chance of a weak La Niña weather pattern developing over the next 3 months. La Niña conditions typically bring higher rainfall and cooler temperatures across Australia, and the study's authors say climate has been at borderline La Niña conditions since mid-November. The agency says La Niña is just one of the climatic patterns influencing our weather, with climate change also having a major impact on temperatures and extreme weather events. One of the longest and most intact segments of Jerusalem's city wall has been uncovered by archaeologists with the Israeli Antiquities Authority. The remarkably well-preserved segment dates back to the Hasmonean Maccabean period of the late 2nd century BCE, some 200 years before Christ, and 800 years before the birth of Islam. The ancient Jewish fortification was unearthed within the Kishel complex at the Tower of David, adjacent to the historic citadel. The newly uncovered segment is over 40 metres long and some 5 metres wide. It was built from massive stone blocks that were finely dressed with a distinctive chiselled boss typical of the Hasmonean period. The authors believe the wall originally stood over 10 metres high. Similar sections of the defensive system have been uncovered around Mount Zion, the City of David, the courtyard of the Citadel, and along parts of the western boundary of Jerusalem, but none are as extensive or as well preserved. A new study by NOAA, the National Oceanic and Atmospheric Administration, has debunked the idea that increases in atmospheric carbon dioxide levels will provide long-term improvements in plant growth. The skeptic's Tim Mendham says, while some increases in CO2 levels are beneficial for plants, too much does end up killing them.
There's a lot of people saying that because we're putting out carbon dioxide as part of our sort of energy activities, and that plants take in carbon dioxide to help them grow, therefore it's a good thing. We're putting out the food that plants use. That's actually, to a certain extent, a little extent, that's correct. Plants do take on carbon dioxide, and there can be times when they flourish in certain environments, but the trouble is you can have too much, and plants can only absorb so much in the same way as the sea can only absorb so much. In fact, it's the sea which is absorbing most of the carbon dioxide that is absorbed. So the trees can only take so much, they can bloom and blossom, and then after a while it'll start to kill them. And then when it kills them, you get drought, so you get less trees and that sort of stuff. Also, of course, when a plant dies, it gives up the carbon dioxide it's been taking in and storing, especially for trees and things like that. So the argument that's being put forward by a lot of people saying that carbon dioxide is good for plants and things and therefore we'll reforest everything is wrong. And this has been shown both in laboratory work and in atmospheric work and satellite photography. So what will happen is that plants will flourish and then die. And when they die, you get droughts, you get low crop yield.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.